Hello, my name is Dr. Johnson. I'm at Grace College. Today is March 16th, 2020. And here at Grace College, we are currently closed while we prepare to go online for emergency distance learning. So I'm working on presenting videos of mathematics while not saying and ah. So this is kind of a fun little thing I'm doing with some of the new coronavirus data and working with Desmos. So here we go. What I've got here is a few days ago on Facebook, I posted an exponential graph that fit some of the COVID data that I'd seen recently. And I found some updated data and I fit it with the logistic model. So just thought I'd let everyone know what's going on here, and they can come visit this. I'll link to this graph on Facebook and Twitter, and so people can come to it and play with the sliders that I've created so they can change things around. So what I have here is the data from Johns Hopkins University, which I linked to there, at least their GitHub page. And I'm starting with data from the 10th because Johns Hopkins University data shows a huge jump between the 9th and the 10th. And then everything seems to follow a really good exponential curve. So I'm wondering if that jump from between March 9th to 10th was maybe an increase in testing, although it could have also been that the cruise ship, so I don't know. But everything since there fits a beautiful exponential type curve. And so what I've done here is I fit a logistic model to the data instead of an exponential curve. The logistic model is something that looks like an exponential curve when things are small, but then it caps off at a certain level. So in this case, you cap off the total number of COVID cases at some unknown percentage of the American population. So I tried to create assumptions, lay out assumptions for this really simple naive model. Our first assumption is that roughly some percentage of the United States population will eventually get sick. So 1/6 of the population got the swine flu back in 2009, and so that's a good default position. Although some experts say that COVID-19 is more contagious and there's less immunity to it in the general population. So generally more than 1/6 of the population will probably get it. So maybe put it around 0.3 or 0.5 or something, who knows? See, I need to stop saying and ah. This is what I'm working on right now. Now, assumption number 2. Well, in this model, we assume no change in social behavior. So this model is like an alternative universe where nothing's closing down, everything's going on as usual. Then we fit a function to these. So these green points right here, those are the real data from Johns Hopkins University. And the blue line is what's called a mathematical model that fits that data. And so the mathematical model we're using is a logistic model where right here, this number, this is roughly the United States population times our percentage p. Put a little there, yeah. Divided by 1 plus Euler's constant e, 2.71828 such and such, to the power of some negative unknown constant times x, and then shifted right or left. In this case, we're shifted right 56 days. Then Desmos fits changes k and a, so that's how it fits the function. It changes little k and little a, so that this blue line most closely fits those points. And if you're curious about how exactly that works, you can take my linear algebra course. It ran this past fall B, and we covered this exact thing of how to fit curvy functions to data points with reducing the sum of squares. Now you see here, this r squared, that means that our function, so if you think about these green dots, you think about their y values, so these numbers over here, they correspond to. So in fact, these numbers right here. So these numbers, you could, as statistics, so it's like middle school level statistics problem is to calculate the standard deviation of those numbers. Well, our function, r squared is the percentage. Our function is predicting the standard deviation of the points. So that means that 99.9% of the standard deviation of the green dots, their y values, is accounted for by our function, which is really, really, really good. It's crazy how good that is. So then we need to assume, we're also going to use our model to make assumptions about how many people will die. So we need two, in our really naive, simple model, we're just going to use two things. There's a lot more, much better, much more complicated models out there. We're just doing a nice, simple model here. So this model will have mortality rate. I think I set the default as 2%, could be 1%, could be 4%. It's not quite known very well right now. And then the number of days that it takes the average person who dies from COVID-19, how many days it takes for them to die after being infected. So this could be somewhere in there. And we're not counting days. So because we're counting in confirmed cases, we're a little bit behind the actual cases, I would guess. And so it's not going to be like the total number of days since dying. It's going to be like the number of days after a person's confirmed that the average person who dies. So maybe 9, who knows. Now, then we now have a mathematical model. So we can use X to let the model show, okay, so at this time, so the model predicts that, if I can use the slider right here, the model predicts that today, by the end of the day, we'll have 4,485 cases. Now, again, one of our assumptions was that nothing changes, and the United States has started making some changes about, not being in large groups, all the sporting events closing down, schools closing down, but also a lot of people are not obeying. Like there's been a lot of people out of the bars celebrating St. Patrick's Day. So some people are social distancing and some are not. It's not sure how much is going on nationally. So it could be lower than this if we're starting to do a lot of social distancing in our country, or it could be right on, who knows. So that X, let's do that. And then if you notice the mortality rate here that we're projecting is a little low compared to the actual mortality rate, because I think it's in the, I can't remember if it's in the 30s or 40s right now. So maybe change our 9 to like 6 or 5 maybe. Yeah, so that bit's better. So then we can use our X and just keep going, but then notice it's disappearing up at the top there. So I need to zoom out and then maybe and then I can move it a little further. Now I can get all the way to 23, March 23rd. Okay, well, now let's zoom out a little more. Okay, now I get all the way to March 29th. Well, zoom out a little more. And then this lets me get all the way to 37th. So it'd be like April 6th. All right, zoom out a little more. And then, okay, so now that lets me get to the 46. Okay. Now I'm still running out, and now I'm in scientific notation over here. So 10 to the 7th would be 10 times itself 7 times, or 10,000. So it's, or no, 10 million. So this would be 20 million, 30 million. So if I had a class right now, one of my students would have raised their hand and corrected me, and I would have said, you get a gold star, but nobody's here. I had to correct myself. So here we are. We finally zoomed out enough that I can reach it up to there. And because we made an assumption, a completely naive assumption that a certain percentage of the United States will get sick, it levels out at that assumption because we zoomed out crazy amount XY. So maybe we should change this window to be maybe x-axis to be -5, delete, to maybe 105, delete, and then change the y-axis. Oh, that's good right there. So that's a logarithmic curve right there. And so what does our model predict about the total people who might die from this disease? Well, that would be maybe about 2 million. So that is a naive logistic model that we created based on real data that makes a final prediction. That's totally not going to be a good prediction because once you start getting out towards here, you basically start predicting what you assumed, which is not good. But it's still fun to kind of play around with this, and you can change what you think the total number of people who are going to get it might be. What if it was all of the United States? Well, then it'd be like that. And you could play around mortality rates, maybe higher and lower. Death falls that many days behind, and then you get interesting numbers. So hope you enjoy playing around this little Desmos page I made, and hope you enjoyed listening to me work on my ums and ahs as I get ready to teach online. Bye.